Hello students, in our today's lecture we are going to start topic 8.9 Earth satellites. Now students, we know that the objects which revolve around a planet, they are called as satellites. Suppose this is any planet and an object revolves around it due to its gravitational force. Then this object is known as satellite of this planet. You might have studied in 10th standard about the planets of a solar system and their natural satellites. So students, once again, what are satellites? A body revolving around a planet is called its satellite. Now about Earth satellites. So Earth satellites are objects which revolve around the Earth. Even Earth is a planet. Motion of a satellite is very similar to the motion of planets around the sun. We know students that the planets, they revolve around the sun. In a similar way, satellites, they revolve around the planets. And so Kepler's laws are equally applicable to them. To them means to satellites also. We know that Kepler has given the laws for the planetary motion, but even that laws are applicable to the satellites revolving the planet. Satellites can be classified into two categories. One is natural satellite and the other is artificial satellite. Natural satellites of different planets, they are known as moon. So moon is nothing but it is a natural satellite. And artificial satellites, they are man-made and they are launched at some distance from the center of the earth to revolve and to gather the information as well as to deliver the information. Now, moon is the only natural satellite of the earth with a near circular orbit. We know that we have only one natural satellite, that is our moon. Other different planets, they have more than one satellites also. Mars has two satellites, Phobos and Deimos. So students, moon is having the circular orbit around the earth. Also, the time period of revolution of moon around the earth is roughly equal to the rotational period of the moon about its own axis, and that is equal to approximately equal to 27.3 days. Means, suppose if this is the earth and if this is the moon, then it takes 273.3 days to revolve around the earth, as well as moon also rotates on its own axis. So its period of revolution on its own axis is also approximately 27.3 days. And this is the reason we see only one face of the moon. And so, due to same period of time of rotational motion and the spin motion of the moon, we see only one face of the moon, that is half of the hemisphere. Next half, which is behind the first half, that we cannot see. Now, artificial Earth satellites are launched as they are useful in the fields like telecommunication, geographics or geophysics, meteorology, etc. Students, we will study more about satellites, that is, their uses and how they are launched, that we will study in our last lecture. Now, suppose a satellite of mass m is launched at a distance r from the center of the Earth and having orbital speed v. So here you can see this figure. In this figure, this is Earth and the whole mass of the Earth is imagined to be concentrated at its center. This is the radius of the Earth denoted by Re. Mass of the Earth is denoted by Me, and the satellite of mass small m is launched at height h. From the center, the distance of satellite from the center of the Earth, the distance of satellite is denoted by r. So it is clear that r is nothing but it is Re plus h. Also, this satellite revolves around the Earth and its speed is denoted by small v. Now students, we know that this satellite revolves around the Earth due to gravitational force of the Earth on the satellite, as well as when any object performs the circular motion, there acts another force on it, and that force is centripetal force. So here we can say that on this satellite two forces are acting. One is towards the center of the Earth, that is gravitational force, and other is away from it, that is centrifugal force. Students, centrifugal is outward and centripetal is inward, but centripetal force is nothing but it is gravitational force. And as both the forces are in opposite direction as well as in same magnitude, this planet will neither move in the outward direction nor move in the inward direction, that is towards the Earth. It will maintain its constant distance and it will revolve around the Earth. That means the distance from the center will remain constant. So now as the necessary centripetal force for the circular motion of the satellite is provided by the Earth's gravitational force on it, we can write that centripetal force is equal to gravitational force. But centripetal force is mv square by r. This we have studied already in our previous chapters. And gravitational force is g me m upon r square. So both these forces are equal. Now simply make the subject v square. So when we make the subject v square, here this small n will cancel, 1r will cancel. So what is remained here on left side? V square, and on right side g me and r. Now this is v square, but we simply want v only, that is speed. So taking square root on both the side to this equation, we get this equation: v is equal to root of gme upon r. But what is r? R is nothing but it is re plus h from equation number 1. So we can write this equation in this way also. In place of r, we can write re plus h. Let us give this equation number 2 so that we can use it whenever it is required. Now let us obtain the formula for the period of satellite. Period means time taken to complete one rotation around the earth, that is the periodic time. Students, we know that speed v is equal to distance upon time. Here I have written. So when any satellite revolving around the earth, when it completes one rotation or one revolution, how much distance is covered by it? If r is the distance from the center, that is radius of this circular path. So if r is the radius of the circular path, then for one revolution it covers distance of 2 pi r. So this is the distance, and we know that for one revolution the time taken is periodic time t. So time t is nothing but capital T. For one complete revolution, time taken is periodic time t. And so I have written speed v is equal to distance upon time. Now this is the speed of the satellite. Even we obtained the speed of satellite here also. So we can compare this equation. We can compare this equation 2 and 3 also. Just we have to square here on both the side. So if we square this equation number 3, then we can directly compare it with equation number 2, because here also it is v square and here also now it is v square. So comparing equation number 2 and 3, we get 2 pi r t whole square, that is square of this, is equal to this term. So this is obtained after comparing these two equations. Now simply open this bracket and make subject t square. So after opening this bracket, if you make the subject this t square, then you will get this equation. Students, sit with a pen and a paper so that you can do these mathematical steps on your own. Now we want only t, that is periodic time, and here it is square of t. So now you know what we have to do. We have to simply take the square root on both the side. Taking square root on both the side, we will get t is equal to root of 4 pi square r cube upon gme. Students, we can do square root like this also, or we can take the power 1 by 2, meaning is same. So rather than putting the sign of square root here, I have simply made the power 1 by 2, that is square root of this term. Now students, here in this equation, this term which is in the bracket, all these quantities are constant. This 4 is a number, pi is also number, which is 3.14. G is the universal constant of gravitation, and mass of the earth is also not going to change, that will remain constant. So all these terms are constant here. So if we remove these constants, then we can write t square is proportional to cube of r, and this is nothing but it is the Kepler's third law. If you remember, we have studied about Kepler's laws in our first or second lecture. So this is the third law of Kepler. Now a note. Suppose students, if this is the earth and a satellite is revolving around the earth, which is very close to the earth's surface. If the satellite is revolving very close to the earth's surface, then the distance of the satellite from the earth can be taken as nearly equal to the radius of the earth. Once again, look here in this figure. Here this satellite is at height h, but if this satellite is very close to the earth's surface and it is orbiting the earth, then its distance from the center of the earth can be taken as re. So here we have considered that thing, that the satellite is very close to the earth, so we can take the distance equal to re. So in that case, what is the period of revolution of that satellite? So let us denote that period of revolution of satellite as t naught. Then t naught is equal to root of 4 pi square re cube. See the distance now. Distance is re cube upon gme. This is the same formula as this. Only what changes we have made? We have only changed this r to re. Now this 4 pi square, if it is taken out of the bracket, so we have to take the square root of that. Square root of 4 is 2 and square root of pi square is pi. So this 2 pi is taken out. What is remain inside? Re cube and GME. When this 4 pi square is taken out, remain is Re cube upon GME raised to 1 by 2. Now this Re cube can be written as Re square into Re. Re cube can be written as Re square into Re. And this GME as it is. Now why I have written this in this way? It is because in next step we know that as GME upon Re square is nothing but it is acceleration due to gravity. Small g is equal to capital GME upon Re. So here also you can see it is GME upon Re square, but it is inverse of this term. So in place of this we can write 1 upon G Re as it is, and this 1 by 2 means it is root 2 pi as it is. So students, this same formula we have written here in terms of small g. Now radius of the earth is 6400 kilometer and value of small g is 9.8 meter per second. So if we put these values in this equation as well as 2 and pi, that is this, and if we'll calculate it after putting these values, if we calculate this, we'll get T naught nearly equal to 5100 second. Now this second can be converted to minutes. How we can convert seconds to minute? Simply divide by 60. If you divide this by 60, now this second will convert to minute. So periodic time of the satellite which is orbiting very close to the earth is 85 minutes. And if you want to convert this minute to hours and minutes, then we know that 85 means it is 60 plus 25, but 60 minute means it is 1 hour, and this is minutes, so 1 hour and 25 minutes. So it is clear that this satellite will complete its one revolution around the earth in 1 hour and 25 minutes. So students, just imagine the speed of that satellite, because it completes one revolution around the earth in 1 hour and 25 minutes. So it is having a very high speed. Definitely this is an imaginary concept. Now example number 8.5. Here given that the planet Mars has two moons, Phobos and Deimos. Phobos has a period of 7 hours and 39 minutes and an orbital radius of 9.4 into 10 raised to 3 kilometer. And here we have to calculate the mass of the Mars from this given data, that is periodic time and the radius of orbit. We have to find the mass of the Mars. Also, we have to assume that the Earth and the Mars move in a circular orbits around the Sun, with the Martian orbit being 1.52 times that of the orbital radius of the Earth. And from this, we have to find the length of the Martian years in days. So now students, let us first find the mass of the Mars. The period of revolution of its satellite, that is Phobos, is given 7 hours and 39 minutes. Also, the radius of the circular path of Phobos is given 9.4 into 10 raised to 3 kilometer. I have shown a figure that this is the center of the mass and this is its natural satellite Phobos, which revolve around the Mars, having radius r of this circular orbit. So now students, we know this equation, that square of the time period is equal to 4 pi square upon gmm into r cube. This is nothing but the Kepler's law only. But here we have to consider the mass of the Mars. If it is Earth and its satellite, then we have to take mass of the Earth here. But here it is Mars and its satellite. So we have taken the mass of the Mars. So this is the equation which we already derived. Let me show you. This is the equation. Now students, here periodic time of revolution is given in hours and minutes. So let us convert this first in seconds, because we know that when we put the values, that should be in SI system. So here this periodic time T is given 7 hour and 39 minutes. So we will convert this hour 7 hour to minutes. So to convert this 7 hour to minute, we know that we have to multiply it by 60. So 7 into 60 and 39 minutes. So plus 39. Now 7 into 60 is 420 plus 39. This will give you 459 minutes. Now this is in minutes. We have to convert this into seconds. So we have multiplied by 60. So now this periodic time is converted to second. It is 459 into 60 second. We have to find here mass of the Mars. So now what we will do? We will just make the subject this mass of the Mars in this equation. So making this subject, we will get 4 pi square into r cube upon gt square. Simply you have to make subject mm in this equation. So this will come here and this t square will come here. Now just put the values 4, then value of pi, that is 3.14, and square of it, r, that is given 9.4 into 10 raised to 3 kilometer. Now we know that if it is 10 raised to 3 kilometer, then that is equal to 10 raised to 6 meter, because 1 kilometer is equal to 10 raised to 3 meter, and that's why this distance was given in kilometer, so we have converted this into meter, so power become 10 raised to 6. So this is the value of r, and as it is cube, so here we have kept cube. G, universal constant of gravitation. T, 459 into 60, and it is having square, so here it is square. T we have obtained in second here. Now students, calculation part I left on you, so you have to do this calculation on your own, and after calculating this you will get mass of the Mars is equal to 6.48 into 10 raised to 23 kg. Approximately this value will be obtained. No matter if after decimal point if you are getting some different value, it's okay, but you will get approximately this value. Now second part, assume that the Earth and the Mars move in circular orbits around the Sun. So here I have shown a figure that this is the Sun and this is the orbit of the Earth revolution. Its distance from the Sun is RE, and this is the orbit of revolution of Mars, and its distance from the Sun is RM. Also here it is given that this RM is equal to 1.52 into RE. This is given condition, and we want to find the time period of revolution of Mars around the Sun, and that is in days. Now students, we know that the time period of revolution of Earth around the Sun is 1 year, and 1 year means it is approximately 365 days. So we'll take time period of the Earth around the Sun as 365 days. Now according to Kepler's law, because we know that planet revolving around the Sun, their laws were given by Kepler. So according to Kepler's law, square of t is proportional to cube of r, and so we can take this ratio that Tm upon Te, and square of this, because here it is square, is equal to Rm upon Re, and as it is cube, so here also it is cube. Students, so whenever there is proportionality, we can take this type of ratio. You might have studied in your lower standard in mathematics that if x is proportional to y, then we can write x1 upon x2 is equal to y1 upon y2, and that's why it is similar to that. Time period upon time period, distance upon distance, and whatever the powers are there, that is to be kept. Now, from this equation number 1, Rm upon Re is equal to 1.52. We can write Rm upon Re is equal to 1.52, and this value we can put here because here it is Rm upon Re. So I have kept that value here, but you can see here we have taken first square root on both the side. So when the square root is taken on this left side, this 2 is removed. So what is remained? Tm upon Te. But on this right hand side, it will become Rm upon Re raised to 3 and root. So it is 2. And that's why we have kept the value of Rm upon Re and taken 3 by 2. Once again, students, let me show you. If I take root of x cube, then that is nothing but it is x cube, that is this value, and root means it is power 1 by 2. Now if you open this bracket here, then what can you write? You can write x raised to 3 by 2. Why? Because 3 into 1 by 2. So it is 3 by 2. So same thing is done here. I hope you understood this. Now simply make the subject Tm, which we want to find here. So I have made the subject Tm. So this Te will come here. So Te is here, and calculating this with the help of calculator, you will get its value nearly 1.87. How will you calculate this? Because it is having power 3 by 2. So first you have to multiply this 1.52 3 times. That is 1.52 into 1.52 into 1.52. So it is cube of 1.52. Then whatever the result is obtained, you just take the root of it, because it is 2 now here in denominator. So in this way you can calculate this and you will get this value. Now 1.87 into Te, time period of earth, which is 365. So here it is 365. Multiplying this two, you will get time period of revolution of Mars around the Sun, Tm, equal to 684 days. Now example number 8.6. To find the weight of the earth, weight or mass. So here we are going to find the mass of the earth by showing two different methods. Students, here given that the acceleration due to gravity g is equal to 9.81 meter per second square, radius of the earth 6.37 into 10 raised to 6 meter, r, that is distance of the moon from the center of the earth, that is r, which is 3.84 into 10 raised to 8 meter, and time period of revolution of moon around the earth 27.3 days. So these are the given conditions, and we want to find mass of the earth by two different methods. Now students, first method, we already know that g is equal to small g, that is acceleration due to gravity on the earth, is gme upon re square. Now in this equation, simply make the subject me, because we want to find this me. So if we make this subject me, this re will move here in the upward direction and this g will come in the denominator. So we get me is equal to g, that is small g, re square upon capital G. Value of capital G, that is universal constant of gravitation, is 6.67 into 10 raised to minus 11, and value of small g, which is given, as well as radius of the earth is given. So simply calculate it and you will get mass of the earth approximately equal to 5.97 into 10 raised to 24 kg. So this is the mass of the earth by using this formula of acceleration due to gravity. Now second method. In this second method, we are going to use Kepler's third law. We know that square of time period is equal to 4 pi square upon gme into r cube. This time period of revolution is for the moon around the earth. So mass of the earth is to be taken. Now here also simply make this subject me. So me will move here and this t square will come in the place of me. So you will get this equation. Now all the values are given to us. Just put these values and then calculate it. You have to calculate this and you will get mass of the earth approximately 6.02 into 10 raised to 24 kg. So students, it is clear that both the methods give nearly same mass. You can see power. The main thing is power here. Here power is 10 raised to 24. Here also power is 10 raised to 24. Only little difference is there in this value. If we will round up this value up to one decimal place, then definitely we will get 6 only. So using both the methods, you will get nearly same value of the mass of the earth. Now example number 8.7. Students, here given that there is a constant k arising in the Kepler's third law. We know that Kepler's third law is square of time period is proportional to r cube, and whenever we remove the proportionality sign we used to put the constant. So here that constant is k, and this k is nothing but it is this only. This is k. Square of time period is proportional to cube of r, so this is the constant. So here this value of constant k in a Kepler's law is given, that take this k equal to 10 raised to minus 13. Its unit is in second square meter raised to minus 3. So first what we have to do? We have to convert this unit which is in second and meter to days and kilometers. Students, these are smaller units. Second and meter, they are smaller unit, and day and kilometer, they are larger units. We know that second is a unit of time, even day is a unit of time, meter is a unit of length or distance, even kilometer is a unit of length or distance. So first we are going to convert this unit to this unit. Now students, 1 second, if we want to convert second to day, then what we have to do? First we will convert this second to minutes. So to convert second to minute we have to divide by 60. So now this is converted to minute. Again, if you want to convert minute to hours, then again divide by 60. Now it is in hour. And now hours to days, we have to still divide by 24, because 1 day is equal to 24 hours. And that's why I have converted this second to days. Symbol is D. So calculating this, we will get 1.16 into 10 raised to minus 5 day. So here we have converted second to day. Also, we know that 1 meter is equal to 10 raised to minus 3 kilometer. So now, simply what you have to do? 10 raised to minus 13 as it is. Now 1 second is equal to this much days. And as it is square here, so we have kept square. And 1 meter is equal to 10 raised to minus 3 kilometer. But as the power is minus 3, so here also minus 3. Now students, here this minus 5 into 2 will be minus 10. So here power of 10 will be minus 10. And here minus 3 into minus 3. So minus into minus plus, and 3 3s are 9. So power of 10 will be 9. And here already power of 10 is minus 13. So power of 10 will be summation of this. And in this way you can calculate. Rest of the things, that is 1.16 into 1.16. Why? Because it is square. So you will get 1.34. And here you will get power 10 raised to minus 14. And so we have converted the value of constant K in days and kilometers. It was given in seconds and meter. Now we want to find the time period of revolution of moon. Students, we already know this formula. According to Kepler's third law, T square is equal to K R cube. Now value of K is here and distance R is given to us in the statement, which is this. So value of K and R cube. So simply calculate this. You will get this answer. Students, here when you calculate this, you will get T square is equal to this value. Then when 10 is multiplied, this 10 is multiplied to this, you will get 758.7 in D square. Unit will be day square because here it is T square. But finally we want to find only T. So just take the square root here. So this will become T. So here also you have to take the square root. So taking square root on both the side, here D square will become D, and simply using calculator you can find the square root of 758.7, which will be 27.5. So approximately time period of revolution of moon around the earth is obtained to be T is equal to 27.5 day. So students, I hope you understood. If you have any doubt or any difficulty in the calculations, you can ask me.